Brandon Brandon is an alumni of Carnegie Mellon University. He graduated in 2022 with a bachelor's in computer science. He also has previously taught as a lecturer at CMU's Introduction to Functional Programming class, which is really awesome. Brandon also, if you go check out, I think Brandon has a lot of really cool projects on his GitHub. Most notably, I thought his coolest project was that he wrote Mulligan, which is a stepping debugger for standard ML, which is really awesome. That's like a really unique project. But of course, Brandon currently is working at Semgrep as a program analysis engineer, working on making application security fast, frictionless, and available to and accessible through all through static analysis. But of course, I will give it up to Brandon. So let's give a big round of applause for Brandon as we welcome.
Great. Thanks, Benson. Honestly, you did your research there. I haven't thought about Mulligan in over a year and a half, but you brought that up, so that's great. I see you all, which is great because otherwise I'd be looking into the ether. I'm not there, physically in person for you. I'm here in sunny San Francisco, and I mean by that I mean foggy and cold. But I couldn't be there in person. I like you guys. I don't like you guys that much. They don't pay me enough to be there, and by that I mean they don't pay me at all. So let's get started with this talk. I've got 30 minutes. We're gonna speed right through it. All right. Sharing is not on, by the way. So we'll let that activate real fast. But as soon as that works, so I'm going to be talking about program analysis, which is pretty cool. Raise your hands if anyone here has taken a class on compilers. Compilers, okay. What I'm going to be talking about is pretty similar to that, but it's a bit of the cooler side of a compiler. So stay tuned. I should be good now, I think. Thanks, Benson. All right, cool. All right, so I know, and yeah, you should be able to see this. Cool. So I know I've got 30 minutes and we're going to speed through a lot of content. We're not going to get through everything, but I just want to give you a taste of what it's like to work on program analysis, which is for software security. I work at a security company called Semgrep, working on making program analysis, static analysis available to people. And I know that you guys have attention problems because like you and we're Gen Z. So every time that I feel like I'm losing your attention, I will switch to Subway Surfers. Okay? All right. So anyways, welcome to my talk. Let's get started, shall we? Oh yeah, I have some cool lights. Boom. All right, let's do it. Cool. So what are we talking about with program analysis? Well, I'm going to go through a few things here, but the first thing I want to talk to you about is software. Now, I'm sure that many of you have dreams of being software engineers. Ooh, I know. But I have to tell you a little bit of history. So on August 20th, 2011, someone named Mark Andreessen published an essay entitled "Software is Eating the World." We're all young. We all have iPhones in our pockets. We know what that means. Software has already eaten the world. There's a lot of reasons for why people need software. The websites that you use, Instacart, Reddit, every single website you've ever interacted with in your life, it exists for a good reason. But software is already in the world. It's everywhere, and it is everything. Now, I don't know about you, but raise your hand right now if anyone here has written a bug in their life. Okay, if you're not raising your hand, you're a goddamn liar. Okay, I'm sure that everyone here has written a bug, and bugs only happen because we write software, and because we're human, we are fallible. Anytime that we write code, we might write code with a bug in it. So the less code we have, the less possibility of writing a bug. So what do you think I'm going to say about the tens of millions of software engineers that exist in the world and the code that they produce? I'm not going to wait for your answer because I probably won't be able to hear you, but the answer is that it is shit. It is shit and it's awful, and there is so much insecure code all around the world, which is why clubs like yours exist, which is why cybersecurity exists. So what can we possibly do about the deluge of awful code? Well, here's a question for you. When you write bad code, what does it look like? I assume that everyone in the room is familiar with Python, so maybe you wrote a program like this. Well, here's where I would again ask, what is the problem with this? But I'm not positive I'm able to hear anyone in the room. So the problem is that this person misspelled their function, right? When they wrote the recursive factorial function, they wrote fact instead of fac. This is not going to run, right? It's going to give you a dynamic unbound name error in Python, right? Or maybe you have something as simple as a type error. I take in a data, which I iterate over, and then I set some kind of dictionary to s.strip for every string s in the data. So like a list of strings, basically, right? Except if you're familiar with Python, basically, there's a dot strip function on strings, but you have to call it with parens, left paren, right paren, like this. Without that, you're just trying to index into this dictionary with a function, which if you have sensibilities, should be kind of a stink in your nose. So why do we do that? What is the purpose of this? These are all mistakes. And they weren't intentional, they were bugs. People didn't mean for them to happen, but they did nonetheless. So most of these seem innocent, right? But a lot of these are indeed able to be fixed, but not all of them can be. Not all of them are fixed because for all of the bugs that happen, we only catch a certain percentage of them. Let me give you an example, okay? I know that AI is all the hype in this day and age, and I know that you're not going to pay attention to me unless I say the word LLM in this presentation. So imagine that you are a machine learning engineer, okay? And you spent the last 6 months working on a state-of-the-art language model, all right? We're going to call it no-cap GPT, and you're ready to test it. So you make a few adjustments, you put some comments, you write some names down, and then you go on vacation to France for 2 weeks. You come back, and here's what you get. Name error. Name modelly is not defined. Did you mean model? This can actually happen to you. This has variations of this have happened to me. You won't know until you run into it. 800 hours into training. That's awful. And people don't mean to make these mistakes, but how do we fix these mistakes that people make, which aren't just security mistakes, potentially, but just flat out mistakes? So, all right, what's the point? Programmers do make mistakes. You are programmers. You make mistakes. You will continue to make more mistakes. Sorry if I'm not the most motivational speaker you ever had. There's a lot of programmers in the world, and these one-off mistakes that happen, and get caught 99.9% of them, there's still that 0.1% that doesn't, right? There's too many bugs in the world, and there's not enough people interested in security, bright young minds like yourself, in college who are interested in security that are going to fix them. There aren't enough of us. So what do we do? Because the cost of these bugs is really freaking high. I don't know if you've heard of this guy called Tony Hoare, but he invented the null pointer, and he refers to it as his $1 billion mistake. $1 billion rested on the fact that he invented null pointers, like dereferencing null in C. I'm sure you're all familiar with. And that was a big mistake because it cost the software industry billions of dollars. This is a war. It is a war upon which trillions and billions of dollars across every industry, because software is everywhere. And it's essential because this is how our society continues to operate. Only if our infrastructure, our tools, our software also operates correctly. So I threw together a little graphic here, but Tony Hoare, we don't like that guy. We don't like that guy. So what's the point? How do we prevent these bugs? How do we make sure that for this overwhelming rush of software that people are pumping out, that it's as safe, as correct as possible? Because the alternative is really terrifying. There's a book called This Is How They Tell Me the World Ends, The Cyber Weapons Arms Race. If you haven't read it, I highly recommend it. I think it's really inspiring for kind of why we are interested in these topics. We need a solution that's going to scale with the amount of software in the world, not the amount of humans, right? We have to tackle this problem at any amount. Software is eating the world. It's time to bite back. Step 2, program analysis. Hello. Hi, my name is Brandon. I didn't introduce myself properly. I'm a program analysis engineer working at a cybersecurity startup called Semgrep. As Benson mentioned, I was educated in computer science at Carnegie Mellon, where I spent 2 years inside during COVID doing math. And that being said, I also went back to teach functional programming. So I believe that you guys have an OCaml course. If any of you have taken that, that's very near and dear to my heart. I work in OCaml every single day professionally. So you're learning real things that have value, is all I'm going to tell you. Semgrep is a startup, and we have an application security platform. And what we were trying to do is make code more secure. Okay, that's pretty much all that needs to be said. The mission here is to profoundly improve software security. I feel like you guys are tuning out. Let me give you some Subway Surfers. Are we good? Yeah?
Yeah.
Cool. All right. Sounds good. All right. Back to it. Mission to profoundly improve software security. Thank you. Make it cheap to make it expensive to exploit software. That is our motto. Today's motto, make it easy to understand why program analysis is hard. So now we're going to talk about the concrete technical stuff. Program analysis is the art of finding undesirable behaviors in programs, usually with computers. We use code to analyze code. And these undesirable behaviors are many. They might be correctness, it might be performance, and it might be security, which is something that all of us here are caring about. But basically, we're writing programs to analyze programs. At the bird's eye view, this is what program analysis is. It's a function named analyze that takes in a program, and if the program is bad, don't. That's pretty much the essence there. If you've ever had a failing CI check in GitHub, this is what that is. Generally comes in one of two flavors. We have dynamic program analysis, which is we try to observe the program at runtime. If any of you have used Valgrind, if any of you have written unit tests, done fuzzing, these are examples of that. So like we take the program and we just run a train of random inputs through it, and then we see what happens. That is dynamic program analysis. But it has some weaknesses because if the dynamic program analysis, if the program loops forever or takes a really long time, dynamic program analysis also will take a long time because if F takes a long time and we run F, we're going to be waiting around potentially forever. And also, notably, dynamic program analysis usually doesn't prevent the code from being written or committed. What I mean by that is if I have a repo, right, in GitHub, and I commit code to it, and then, tests run, that didn't stop me from committing the code at all. The idea of shift left is that we want to make sure that all of our security checks happen as far left forward in time as possible. Just real fast, raise your hand if you've heard of shift left. Okay, it's common vernacular for me at work, but I work in cybersecurity. So shift left is the idea that we want to move our checks as far forward in the future as possible. Before you even write your code, before you even commit your code, let's figure out if it's wrong. Static program analysis is about finding out properties of programs without ever running them. And I have a little motivating quote for you that I ripped from Wikipedia that I'm not going to quote here, but a costs to fix in development are 10 times lower than in testing and 100 times lower in production. When you test in prod, you are costing your company 100 times more dollars. And I know money, whatever, but like this matters. Okay, this is worse for how you're going to develop, and this is worse for your company for whenever you eventually get jobs. I trust you. You can do it. I believe in you. Don't go on r/CS majors. It's a bad idea. They're bad people over there. Okay, so that's our focus for today. Specific applications for static program analysis, for instance, include something called SAST. Raise your hand if you've heard of SAST. Static application security testing. It's just using static analysis on code to figure out if they're bad. I might also say that certain other applications of static program analysis include syntax highlighting, which is looking at a program and trying to color it. I think that's a kind of static analysis. Also type checking, right? If you've ever used C or Java, they have static type checkers that will look at everything and try to figure out if you did like an oopsie and did a fucky-wucky and fucked up your types. All right. So my analogy for you is this, okay? A computer program is like a loaded pistol. If I suspect that my pistol might be defective, I can just shoot it and see if it blows up in my face. I can just straight up go, and I could fall. But that wouldn't be very fun. That'd be kind of embarrassing. So let's not shoot the pistol and figure it out at runtime if it's going to make shit blow up. Or if I wanted to be a little more thorough, a little bit more scientific about it, I could inspect the pistol for damage. I could check it and see if someone put .50 AE in a 9mm pistol. I'm from the South. I don't really know what that means, but it means big pistol and small gun. Okay, or big ammo and small gun. Okay. Now, the solution that doesn't end up with me on the floor, okay, and the pistol exploding in my face, obviously is the preferable solution, right? So let's try, by analogy, this is our analogy for why we should understand that static analysis is preferable, okay? And basically what I'm saying is that we need better solutions than just running into errors blindly in prod, okay? If I discover that there's something wrong with Curiosity after it took off, like, that is terrible. If I figure out that it happened before it took off, that's a miracle, okay? I'm a hero. Let's not kill people on the rover. Well, actually, I don't think Curiosity had people on it, but like, let's not, doom the experiment, okay? So shift left, I explained this, All right, far left as possible. I'm not gonna make it political. Yeah. Anyways, so here's the SAS tools perspective. I wrote this little comic here, you see. Hello, is your program running? And the static analysis tool says, no. And then the person on the phone is like, oh, that's okay. No cause for alarm. It's an anti-joke. It basically just, yeah, I think it's funny. Anyways, you guys need another dose of Subway Surfers. If I had a lot of time to prep for this talk, I would have actually done it with like the captions and everything, but I didn't. So just let's subsist off of that. Okay, but before I can delve further into program analysis, I have one very small issue for you, tiny, minuscule, really, which some of you may know what I'm going to say next. But program analysis is inherently impossible. How many of you have heard of Rice's theorem? Actually, you might have heard of Rice's theorem, but you know what? Yeah, I'm sure you all know what it means, right? All non-trivial semantic programs, properties of programs are undecidable. What that means is you cannot definitively answer yes or no for any property of a program's behavior in a finite amount of time. This is classic undecidability, right? Classic computability theory. We can't do program analysis, not without running the program. So that sucks. All right, see you guys next week. No, we still have other stuff to talk about. This is a corollary of the halting problem, which I'm sure that all of you are familiar with, which is that we can't tell if a program halts or not, right? We can't do it. The reason why is because if we assume that we can tell if a program halts, this program, I would again ask you if you knew what this is, but whatever. The point is that this is a paradox. So foo is a function that if foo halts, then it loops. Otherwise, if foo does not halt, then it halts, right? This is a classic Epimenides paradox, kind of like this sentence is a lie. It's a paradox. We can't solve the halting problem because what should that program do? What would this program return? So we cannot definitively answer the halting problem. So because we can't do that, because any program can loop forever, that means that any program, any property that we want to answer with program analysis can't be done. Well, what do we do about that then? Well, because obviously there's more to say about this talk. It only sucks if you're a quitter, is the end result. We only are done with program analysis if you're a goddamn quitter. And my mom told me not to be one of those. When you're solving a hard problem, there's two signs that are true. Either you're not working hard enough or your expectations are too high. It's like when I told my mom I wanted to be an Olympian when I was a kid, and then she laughed at me. That's because that'll never happen. But maybe your expectations are too high or you're not working hard enough. In this case, the impossibility is a mathematical truth. It's not a skill issue. It's not our fault. It's not that we weren't working hard enough. It's that our expectations are too high. This is the same I just gave you. It is impossible to definitively answer yes or no for any property of a program's behavior in a finite amount of time. The main innovation that we're going to talk about is it's only impossible to do program analysis if you insist on being right all of the time. We don't always have to be right. We can sometimes be wrong. That's okay. Now, this is probably weird, okay? Like, if you went up to your TA and you were like, oh, yeah, like, sometimes we're allowed to be wrong. You should give me the points. Like, they'd probably laugh at you, right? That's not the same thing. And any product on the free marketplace is probably going to, be condemned to bankruptcy if they don't work just flat out some of the time. But thankfully, with program analysis, this is legitimately an impossible problem. The best we can do is solve it some of the time. So unlike, your pathfinding algorithms, whatever, we don't have to be on all the time. Program analysis is an approximation. That's what it is at the end of the day. So program analysis sometimes lets you, when it always completes in a finite amount of time, sometimes they are inaccurate, sometimes they're incomplete, or sometimes they say yes, no, or I don't know. I don't know is a perfectly fine third thing to say in program analysis. There's this other corollary called the full employment theorem, which basically says there's always jobs in program analysis and compiler writing. But actually, I don't care enough to talk about that. All right. So for instance, like let me motivate this to you a bit more, which is that like I'm perfectly allowed to write this program, right? Halts. What it does is it takes in a Python program as a string and it returns an optional bool if it halts, right? So if the program is x equals 1, we return true. If if it's x equals 2, we return true because these all halt. And if it's while true, hot pass, then we return false because that loops forever in Python, right? No one says we can't do that. But like think about all of like the infinity -3 programs that we left out in this case. We still haven't captured every function. So what I'm saying is that we cannot solve this halting problem in generality, which I think you probably know. And another fun corollary of this is that if you had like a team of monkeys at typewriters, eventually they could write a better halts function than existed anywhere else. You might think that this is demotivating. I actually find it inspirational. I don't know why. Okay, so this is the scope of our task, program analysis. There is finite time and there's finite resources, and the problem, I've told you, is already defined to be impossible. And software is eating the world. The cost of failing is pretty darn high. So let's put in some elbow grease and get to work. Number 3 is implementing the impossible. So how do we actually implement program analysis? Let me give you a very concrete example, which is called type checking, okay? Unless you've used Python for your entire life, I expect you to know what type checking is, and if you have done that, then I'm sad for you. Let's suppose that we are solving the problem of adding two ints, okay? We might say that the function that adds two ints and produces an int has a type which is like int comma int to int. Automatically determining this with computers is the problem of type checking, okay? Being able to look at code and say that takes in two ints and returns an int. And a type is something that something might be. That is as specific as I will get with it. Let's consider the problem of typing // which in Python is the floor division function, okay? It takes two integers and computes the integer division. So like 3//5 will be like, I guess, 0. So we might say it has type int two ints and then goes to int, right? Because it takes in two ints and returns an int. That's cool enough, but like what is one caveat about the division function? The one caveat is that if you pass in 0, it blows up in your face. Everything dies, prod gets broken into, and then your manager fires you on the spot. Okay? When you divide by 0, bad things happen and you no longer have a job. So that's what we call a dynamic error. We want to catch these errors before they ever happen. So can we somehow give // a type that will prevent us from ever running code that passes 0 to it? As in, statically, before we run the code, it will know, oh, you're going to eventually divide by 0, and it stops us. Can we do that, is my question. So there are two properties that we want to have of such a type, okay? One is that we should be able to figure out the type in a finite amount of time. That seems to speak for itself. Okay, you shouldn't want your type checker running forever. And then 2 is that you should be able to say that x/y is ill-typed if and only if, like, legitimately it is ill-typed or we passed 0 to it. As in, there shouldn't be, like, false positives. It shouldn't, like, say something that isn't true, okay? So it should be correct, and it should always terminate. Does this make sense to everyone? I'll take questions now, by the way, also, if anyone has. Okay. The problem with program analysis is that it's impossible to have both of these things at the same time. You cannot have your cake and eat it too, which is what a dear friend, the Unabomber, used to say. So when it comes down to these problems, you have the choice of looping forever or being wrong, but you can only ever choose one of them. You cannot, yeah. So you cannot have neither of them, basically, is the problem. Raise your hand if you've ever heard of dependently typed languages. Could be your standard Idris, your Lean. Okay, that's fine. It's more of a thing at CMU. Basically, there are languages that have really sophisticated type systems where you can actually express, hey, you can't pass 0 to this function. But they're really, really advanced. And the problem is that type checking can take forever. As in, you can be compiling your program and it will loop trying to solve the types. I'm going to call that a type A program analysis, whether or not you use it and you don't necessarily terminate. The other track is that we do terminate, but we're sometimes wrong. That's called a type B program analysis. So sometimes we'll reject programs that are correct, or sometimes we'll accept programs that are wrong. So type B is wrong. Type A sometimes loops forever. Let me give you an analogy for this. You are in charge of security at an airport, and you are well aware that in the early 2000s, a man tried to set off plastic explosives in his shoes on a transatlantic flight from France to Florida. Now, you know that you don't have a good way of telling if anyone has explosives in their shoes. Your metal detectors don't go to the shoes or whatever. So what do? What is the solution to people potentially having explosives in their shoes? Well, this is why everyone needs to take off their shoes in an airport. The easy solution is that you assume everyone has explosives in their shoes. You say, all of you have explosives in your shoes, take off your shoes so I can scan them. The point is that instead of giving a precise answer, determining everyone who has explosives in their shoes, you assume an approximative answer. Everyone has explosives in their shoes. So by analogy, if I wanted to tell if a program had an unsafe call to this division function, I would just use this function here. What it does is contains unsafe division, takes in a program as a string, and if it contains // we say that it's bad. This will work, right? Like, sometimes. It'll sometimes work, but not always. So let's check it, okay? Contains unsafe division on the x = 2 program, returns false. That's true. It doesn't have an unsafe division. On 1 divided by 0, it returns true. And that's true. It does have an unsafe division. On 1 divided by 1, it returns true, and it doesn't have an unsafe division. And on a comment saying https://google.com, it also says that that contains an unsafe division. That's this thing right here. So sometimes it works. But that's what type B analysis is. We accept that we're wrong sometimes in exchange for the fact that it always completes, it always terminates. So which should we prefer? Should we prefer to loop forever, or should we prefer to be wrong sometimes? Well, the answer is that in the context of type checking, the answer is neither of them. If I wanted to do this, if I shouldn't want to have to loop forever or be wrong sometimes. That kind of sucks, right? With more sophisticated program analysis techniques, we could be a little bit better than like this // substring thing I just told you about, but like not by much. We couldn't be much better. So the right solution is actually we downscope. We decide that it's not worth the trade-offs to care about division by 0 this much, because division by 0 doesn't happen that often. So basically, the point I'm trying to tell you is this part here, okay? Type C analysis is where you stop trying to solve the problem you're originally trying to solve. You just set your sights a little bit lower. You lower your expectations. So for the problem of does this program divide by 0, we're going to instead employ a type C analysis where the answer is I don't care. I'm just not going to solve that problem. I'm going to solve an easier one. So the question of does this program divide by a non-integer? That is an easier problem, and we can do that all the time and always be right about it. But we can't say you divide by 0 specifically. But we can say, oh, eventually you will divide by a bool, right? If you use Java or something, you are not going to divide by a bool unless you do like some weird casting bullshit or something. I don't know. I don't actually know Java very well. Okay. So this is solvable in a terminating manner, okay? That's because non-integer is like pretty broad, but 0 is very specific. So let me recap really quick. We want to answer questions about programs, which are impossible to do in general in finite time. We have to give up one thing among guaranteed termination, perfect accuracy, or solving the specific problem that we set out to solve. And types A, B, and C analyses, which is a term I made up, by the way, in case you're writing this down for the test, they correspond to giving up each of those things respectively. So dependent type checking is type A because it can loop forever. Rejecting every program that has // in it is a type B analysis because it rejects potentially valid programs, right? And then regular type checking, as in not being able to catch divides by 0 statically, that is a type C analysis. We just decide we don't care that much about division by 0. And for most practical program analyses, looping forever is not an option, okay? If you've ever run a CI pipeline and had it run forever on you, I'm sorry, that sucks. You shouldn't want that. So usually we're, in program analysis, we are concerned with type B and type C analyses, okay? Let me recap to you with pictures. So I like to envision it as 3 kinds of people. A type A analysis is an old person that might take forever to answer you. A type B analysis is a flat earther. They might just spout nonsense at you and be completely wrong. And then a type C analysis is a literal child. They can only answer very simple questions. That is pretty much the way to remember this. So types A, B, and C analyses are kind of the bread and butter of program analysis problems and that we're trying to solve. How am I doing on time, by the way, Benson? Is he still here?
Yeah, 10 more minutes if that's okay.
10 more minutes. That's great. Okay, cool. I just wanted to make sure I wasn't already over because I wasn't actually taking attention. Okay. Okay. Any questions about this before I move on, by the way? I will take questions in case anyone's confused.
Looks like no question. Oh,
cool. Sounds good. Okay. Cool. I have high choose here, and I would give them to you, but I can't. That sucks. All right. The life cycle of any program analysis begins, as many things do, not with a bang, but with a text file. The typical stages of program analysis are as follows. We have lexing, which takes in a program as a string and outputs what's called a token list. And I'm talking about implementation now, by the way. I'm walking you through how program analysis tools are typically implemented. So we take in a string and we output a token list, which kind of groups together the fundamental units of a program. Then we do parsing, which takes in a token list and outputs an abstract syntax tree, which is a tree representing the program structure. We have an intermediate representation, which turns the abstract syntax tree into abstract assembly, which kind of like gets closer to the fundamental things that are happening. And then we do analysis, which makes use of classical analyses like things like data flow analysis, pointer analysis, symbolic execution. If you've taken a compilers class, you probably have heard of most of these things. These are kind of like the front half of a compiler, I would think of it as. And I have a nice little photo here for you, or a nice little picture here for you for how you should visualize this pipeline. So we take in the text, we go through lexing to the token list, we go through parsing to the AST, and then we go to a control flow graph, a CFG. I'm going to run through it really quickly because some of the stuff is not super interesting, but some of it is. So basically, all right, lexing. Let's think about it this way. Lexing is how we take the source text, like a Python text file, and turn it into a token list. Here's how you should think about it. If I have this and I'm rushing because like this is originally like an hour's talk, but I'm trying to get you as much through this. We're not going to finish, but that's okay. This Python program is just this thing. If we wanted to lex it, we would group together all of the parts of it that seem the same. So what I mean by that is, similarly to how when you analyze English, you might group together all of the words as opposed to looking at everything like characters. When we lex, we decide to see the program not as a string of characters, but as a list of fundamental units. So every colored thing here is its own token. So we turn like to into its own token and foo into its own token and return into its own token until we get a list of them. That is breaking it down into words instead of characters, right? We see the forest instead of the trees. So after tokenization, we might get something that essentially looks like this in some programming language. If you ever use Rust, you would do this with an enum. If you've ever used OCaml, you would do this with an abstract data type. An algebraic data type, so on and so forth. But this would be essentially be your list. You have an id, which contains the data of x. You have an EQ symbol. You have a num of 2. You'd have a minus, so on. That's all. I'm going to move on because the process of doing this is extremely boring. No one cares about that. Caveat for the eagle-eyed among you, which is that in Python, this is actually more nuanced because you have to deal with white space. But I don't care about Python, so we're going to move on. I'm going to give you another dose of Subway Surfers. We good? Cool. All right. Great. All right. Parsing. We take in the token list, the words of the program, and we turn it into what's called abstract syntax tree. Raise your hand if you've heard of an abstract syntax tree. Okay, some of you may have come across this, particularly if you've taken a programming languages class or a compilers class. One of the most fundamental discoveries of the 19th and 20th centuries was that light is both a particle and a wave. I'm going to tell you that programs employ a similar existence, which is that programs have a dual existence as both text and trees. So if you've ever heard of abstract syntax trees, text is cool. Text is good. All right, let me walk you through some pros of text. Text you can edit on any application in an application independent way, right? You can use Nano, you can use Vim, you can use Emacs, but if you use Nano, we hate you and you should not be here. You can search and refactor it at scale. It's a simple data format. All of these things are good things. Cons is that you cannot analyze the semantics of text very easily, right? It's very easy to make typos, and you have to validate it before you run it through a program or a compiler every time. For instance, let me give you this program, okay? Suppose that we're interested in a fake synthetic problem, which is finding out if a Python program ever prints 0, okay? And this is a standard. It's a fake problem, but this is actually similar to solving this is similar to solving other problems. So if I do print of 0, has 0 print, right? This would work for some programs, but what's wrong? A lot of things are wrong, right? This does not, for instance, work on if we assign 0 to this is0 variable and then print it. This will return false because it literally checks for the literal string print of 0, right? What if I put a new line in? This also doesn't work, right? Because now there's a new line. It's not literally print left paren 0 right paren. Text is a really bad way of representing the structure of a program because it doesn't show you the semantics of it, really. It doesn't talk about what the program means. So let's go hug some trees. This is more popular in San Francisco than in LA because you guys have no public transit or something like that. I was there recently. Let's consider this analogy. Have you ever done the classic reverse Polish notation op trees problem? This is a pretty classic stack-based calculator problem. Basically, if you've ever implemented a calculator, there's this thing called op trees. So you can represent arithmetic expressions with trees. This, for instance, is how we would represent 1 minus 2 plus 3. That's because 1 and 2 have a parent, which is minus, so 1 minus 2. And that has a parent of plus, so that is added to 3. There's an implicit parens around this subtree. If you squint your eyes, I think it should make sense. This is what we call abstract syntax because if we look at this tree, the parens are nowhere to be found. We don't have the parens anymore because we're just talking about the abstract syntax, not the literal syntax. It doesn't matter though because the tree tells us what the program means, not what the program literally textually says. So we call this an abstract syntax tree. We can also do this with programs. So if I have this Python program, x equals 1 minus 2 plus 3, I would say that we denote it with this abstract syntax tree. It's an assignment where we assign x to the rooted subtree, which is the expression we just saw, right? 1 minus 2 plus 3. That is the subtree, and that is the expression we assign it to. So but notice that we've gotten rid of a few things. We don't have the equals around anymore because it's implied by the assignment. We don't have the right paren and left paren because it's implied by the structure of the tree. It's abstract. But we can do this for programs is what I'm saying. Actual Python programs are just trees. If I look at, for instance, for our example, a running example program, which was the thing we saw earlier, we would actually denote it by this tree. X equals 2 minus 1, and then there's another thing after it, which is the def foo, which takes an x of type int and returns 5 plus x. I can read these really quickly because I work in these. Maybe this comes a little less naturally to you, but if you squint your eyes and go with the vibes, you should get it. That's generally how program analysis works, is you go with the vibes. So work with me here on that. But if you squint your eyes and look at programs, essentially they should look like trees. What am I getting to here? What's the point? When we parse programs into abstract syntax trees, we can conduct analysis on it easier. I can ignore how the program looks and focus on what the program means. If your parents ever told you not to judge a book by how its cover, that's what this means, okay? Yeah, abstract syntax trees let us do that. So for instance, if I had an abstract syntax tree representation, I could check for returning 0 by doing a more sophisticated thing of where I check if the node is a return, and I check if there's a return of 0 because the child of it would be 0. And I don't have a diagram for you here, but I should. But the point is that this will help us do a little bit few more cases. Focus less on the indentation and the new lines. But there's a little bit of an issue with this, which is that it still doesn't work with cases where we assign the variable to 0. I know I didn't give you a whole lot of time to look at this code because I'm kind of rushing, but basically this is still too naive for some use cases. So it lets us ignore some of the syntax, but it doesn't tell us the entire story. We'd have to do something called control flow analysis in order to do this. I'm just about out of time here, so what I'm going to do is I'm going to show you a few examples of control flow graphs and then wrap up there. Basically, I don't have a whole lot of time to go through this, but basically the idea, and I knew we weren't going to get through this. I have a Chapel Run reference here, just in case any of you are fans. Anyways, basically we could take a program like this that has x equals true, y equals 2, if x equals false, else y equals 3, and we turn it into a pretty graph like this. We determine whether or not it's possible to make it from here, the if x, to the x equals false, or if it's not true, then we go to y equals 3. And we can do this in an automated way on any program. So what happens in program analysis is we take our programs, we turn them into abstract syntax trees, and then we turn those trees into graphs like this. And then we do kind of a graph traversal using a technique called data flow analysis, which I won't have enough time to explain, but is a kind of bread and butter compilers technique. Okay. You can go look at any kind of compiler textbook to find out more about it. These slides will also be posted after. You can look in like Appel, modern compiler construction in ML is pretty good. I'm not gonna have time to go through any of these basically. I know I basically went through everything really freaking fast. I didn't have time to go through everything. But the point I'm trying to get across is I hope that you're interested in the stuff that has to do with program analysis, because I know this is like a security thing and it's like a little bit different, but like security is basically founded on the notion of like being able to conduct analysis on programs at scale. If any of you become security engineers, you're going to be using SAS tools, security software analysis tools on a daily basis. What I want you to know is I want you to know how those tools work, because how they work under the hood is actually not super obvious, and they're not always right, is the thing you have to know at the end of the day, right? And I know that okay, the way I have to say this to you is part of growing up is learning that your guardians are not perfect, okay? And neither are your program analysis tools, okay? And they're fundamentally flawed. I told you that the program was impossible. The problem was impossible. I don't mean to tell you like, oh shit, like you should like find a new job. You know what I mean? Like I'm not telling you like go to like ACM AI or whatever instead of ACM Cyber. Like cybersecurity is pretty cool. But what I'm trying to tell you is that be aware of the fact that the problem that we're trying to solve is a worthwhile one, because the hardest problems always are. The fact that it's impossible means that the best we can do is try to approximate it and minimize the noise. So security is a war. And in the words of the famous G.I. Joe, knowing is half the battle. Okay? I don't know if you guys are too young to get that reference. I really hope not. I hope that through this presentation, you've learned a little bit, not a lot, about static analysis, about how people might use it in security. And what you really need to know here, though, is like there's a lot of code in the world. I kind of stressed that to you at the beginning. And the need for better guarantees about security is going up, right? We run and deploy so much code that it's criminal. Okay? Today's world of security is not the same as tomorrow's, but if you maintain knowledge over how these tools work, if you are resourceful about how you learn about application security, you're going to have a long, fruitful career in it, if that's what you so wish. Okay, and knowing about how static analysis works is the first step in that. So all that's to say is that the goal here is to make static analysis fast, fruitful, and frictionless, and to make code a little bit more secure. This has been a haphazard jumble of things, but thank you for listening. That's it. I also didn't go too much into my career in cybersecurity. So if you're interested in actual cybersecurity, like job-related, career-related things, I will also answer questions about that. But I think that Benson, I think it's cool if we do a little Q&A now.
Yeah. So thank you so much, Brandon. Really awesome talk. Anyone have any questions for Brandon real quick?
I'll take questions related to like the topic or also on like cybersecurity in general, application security. I've worked in this field for about 2 years now, so I know a little bit about that.
Yeah, we have a question from one of our co-presidents, Jason, actually. Jason, go ahead.
So wait, first of all, can you like hear me fine?
Can I share the slides? Yeah, for sure.
No,
no, can you hear him okay? Or
oh no, apparently not. Apparently not.
Okay, come closer to the microphone.
Yeah, I don't bite. I'm virtual.
Okay. So I guess like in terms of being wrong, there are like two types of being wrong, right? There's like rejecting incorrect, or there's rejecting correct programs and accepting incorrect programs. And while it's not possible to avoid both, you can avoid one of them. So, like, does Semgrep take a stance on this? Like, which one do you prefer? Or do you like do both, or whatever?
Ideally, the idea is that you should have none of either, right? Okay, so false positives are a bad rap because if you get false positives, that is to say, you say something is bad and it's not, your application security people that are using your tool are going to get real mad at you. They're going to be like, what the hell? This is fake. You wasted my time. Obviously, that's bad. But if we say that something isn't a problem when it is, that's a false negative, that is also bad, albeit it's a more silent kind of bad. The thing is that later on, if you get hacked and like we didn't catch it, that's on us. So to some extent, like false positives are worse, like in terms of PR, but we're both bad at the end of the day. People who work in like the government, like people who work on like NASA, they actually employ a really false negative. Uh, they don't want false negatives at all because they will like take all of the noise that you can give them because they can't chance there being a single actual wrong thing. So that's a pretty interesting question. But the answer is that it depends based on your use case. We try to minimize both.
All right, thank you.
Yeah. 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 Anything else?
Some other questions? Yeah, Gary in the back. Do you want to come up a little closer? Sure.
In the meantime, I can do this little bit that I forgot to do, which is that I was going to be like, static analysis is good. Oh, fuck. Static analysis is good. And then dynamic analysis is bad.
I think your Zoom microphone is muting your piano playing, but I think we get the point.
Motherfucker. I was playing a major and then a minor chord. All right, it's fine. What's up?
What do you think about using LLMs for binary analysis, such as passing the intermediate representation into like ChatGPT or something? It's
So I guess Gary's question is, what do you feel like? How does like large language models compare to like a lot of classical program analysis?
Yeah. Do you say LLMs? Wait, sorry.
Yeah, Gary said LLM specifically. Like, oh, did he? Oh wait, okay, I get it. No, he loved it. All right.
Was the bit worth it?
Yeah.
Okay, great. So that's a good question. Actually, I work on the AI team at Semgrep now. So I used to be a doomer about AI. I actually kind of really hate AI. And LLMs are stupid, but useful. The hype around them is stupid. But the point is that there's a lot of really cool things happening with AI and cybersecurity right now. The problem is that, AI, obviously, is non-deterministic. That is one big deal about it because when you have a security tool that gives you back non-deterministic results, that is really bad. As in, like, you scan your code once and it says you have a problem on line 5, and the second time it doesn't. Like, that's one way to just kill your trust in the tool because you won't be able to trust any given finding that comes from it. There are applications for AI in program analysis, if that was a specific thing you were wondering, but um, feeding like code into an LLM and asking it whether or not like there's bad stuff in it is a stupid fool's game. We actually had like a person come to us who was like, "Hey, yeah, like we just fed our code to an LLM and we think it's better results than Semgrep." And I was like, "Show me the proof, bitch." Like it was so they were wrong. They were wrong. It was just there are things you can do. And I work on a specific problem, which is using AI to auto-generate what's called Semrep rules, which are basically queries you can run in Semrep's engine. But I wouldn't hold a lot of like water with like feeding your whole code base in an LLM and then asking it for magic genie results. Does that answer your question?
I agree.
Yeah. All right. Cool.
Any other question? Yes, Salma, you want to come up?
Very quick, like meta question. Would you use Semgrep to analyze Semgrep?
Yeah. What do you take us for? Charlatans? Oh, yeah, that's called dog fooding when people do that. They run their own product. For instance, used to work at Facebook. Facebook's internal messaging platform is Facebook. So that's not really a joke. So yeah, we use Semrup internally. Anything else?
I'm going to ask a quick follow-up question to what Salma just asked. So, Brandon, I know you've worked on a lot of really cool projects at Semgrep. One of the really funny ones I read like on the Semgrep blog that you worked on is if you guys have ever used CodeQL. Before CodeQL is a
Uh,
competitor for Semgrep, and I believe Brandon, you worked on as like an April Fool's joke. You guys added analysis of CodeQL queries into Semgrep. So I'm not sure if you
yeah.
can talk a bit about like what was the inspiration behind that, and also a little bit about like what you did on that. I know that you have the blog post out there that folks can read as
It
well.
was yeah. So CodeQL is a scanning tool that's not us, and they have queries written in a particular language. And I implemented support for Semgrep to scan those queries. To be clear, there's no value in doing this. It's just funny, because we say that we scan our competitors basically. So the inspiration is that I was out at a bar with some of my coworkers, and we were just shooting the shit, and then we were talking, and there was someone was like, "Wouldn't it be really funny if we supported CodeQL as one of our languages? Because we support like over 26 languages. We use a technology called Tree Sitter. It's pretty easy to add languages to Semrep." And then I was like, hold my beer, except not literally, but the next April Fool was basically I decided to do it. So that was basically the inspiration. I'd say that's the funniest project I've worked on. It only took me like 2 days. It's pretty easy to add languages to Semrep, and I'm pretty advanced. I'm pretty like used to it now. But yeah, that's kind of the one of the things I've done for shits and giggles at Semgrep. We also had a Halloween costume contest once, and we got a gift card as a gift, and I asked them to give me a Fortnite gift card because I thought it'd be funny. So that was another thing I did once. I got V-Bucks. I don't play the game. I don't play the game. I just don't use gift cards, and I thought it'd be funny.
Awesome. Any final questions for? Oh yeah, Andrew, you want to come up to the mic to ask Brandon?
I guess just one more question since you mentioned Tree Sitter. Have you are there any other applications of Tree Sitter that you've been interested in recently or anything? Because I've heard that Tree Sitter is being used in code editors now, and I wondered if you had any thoughts about that.
Yeah, so the Tree Sitter toolchain is an open source series of parsers maintained by the community. They're all open source and they're all good parsers for every language you can imagine, JavaScript, Java, Python, whatever. They're used in a lot of things. I would say that yeah, indeed they run in any single one of your editors. If you use NVim, you use the syntax highlighting, better syntax highlighting features. Those are all Tree Sitter. I would be very surprised if any application that implemented syntax highlighting, think CoderPad or I don't know, even the things you use to submit your assignments, Gradescope, they probably all use Tree Sitter. I'd say that that's the main thing I'm aware of. Most program analysis tools probably also make use of them just because it's a real time saver. If you had to go and implement parsers for every single language, good luck trying to parse ANSI C, okay? It's a fool's game. It won't end well for you. So I'd say that's the main use case. Parsing is not so interesting of a problem, so we can kind of all band together for it. But everyone implements their own custom analyses on top of that, usually in the program analysis world. Yeah.
Great. Any final questions for Brandon?
Yeah. If you all are afraid for your futures and your careers, they'll take questions about that too.
I don't see any more hands raised, Brandon. So I'll end on one really fun question, Brandon. So I know, Brandon, you during your time at CMU, you not only were really interested in functional programming and program analysis, but you also were really into theater as well. I saw on your website. So I was wondering if you could share what is your favorite musical, or I guess what is your favorite work in sort of theater?
Right. It's been behind me this whole time in case you didn't see, but oh fuck, I gotta go backwards further. All right. So all right, in front of on top of my guitar, fucking hell, it's reversed. These are my playbills, and my favorite musical is one called Come From Away. And there's no good way for me to describe this, but Come From Away is a musical about 9/11. And I know what that sounds like. I know what that sounds. You there in the front, don't laugh. All right, I see you. I know it sounds. No, the idea is that on 9/11, when what happened in New York, there were 38 planes that were going to North American airspace, and then North American airspace was closed. So what did those 38 planes do? Because it was closed because of 9/11. So what happened on the day was that those planes were diverted to a small town in Newfoundland, Gander, in Canada. And the story is what happened that day in that town when a truckload of people came into the town, thousands upon thousands of people, without food, without a care, with terror in their hearts, and kind of the community that uplifted them on that day. So it's one of my favorite musicals of all time. But I'm definitely a musical theater nerd, by the way. So this is you really nerd cite me with that question there, Benson. Thank you.
All right, awesome. Thank you so much again for coming to give a talk. A lot of fun, really awesome stuff. Let's give one more big round of applause for Brandon.
Great. And I'll
yeah,
add-
we'll share the slides and we'll post them later on our Discord video. But yeah, thanks so much, Brandon. Thank you for coming.
Cool. All right. One last thing I want to say, which is ask Rathul how his time went at Semgrep because he's going to be interning for us. Also, I came here to teach you program analysis. My real love is functional programming. So find my website, brandonspark.github.io, because I have lectures on functional programming there. And my biggest joy in life is for people to learn more about that. Thank you so much for having me. I don't know, have a skibbity day or something.
Thanks so much, Brandon. Take care.
All right. See y'all. Have a good day. Bye.